Hi, today I will teach you about uh, how to design a finite impulse response filter using Matlab. Okay, first I will give you some introduction what is finite impulse response. Okay, finite impulse response FIR have the differential equations. Okay, for the filter is generally appear in this form. Okay, this is the format. So we will have yn equals to b naught is our coefficients, xn, okay, xn is our input, and plus with b1 coefficient xn minus 1 and continuous until n minus m. Okay, from here we can see that we have the yn is our present input, and we have our b naught xn is our present input, and we have the xn minus 1 minus 2 until minus n is our past input. So we can see here, because these signals, this transfer function yn is present output is depend on the present and the past input. So this system we call as a non-recursive system. It obviously that the FIR is a subset of more general IIR. Okay, so we can have two types of realization structure of FIR. Okay, first one is a direct form. Okay, this is direct forms when we have a signal, when we have a transfer functions for our filter, hash jack 1 plus 2z minus 1 minus 3z minus 2 and minus 4z minus 3 plus 5z minus 4, and it just directly plot out. So how we directly plot out is we have the input xn divided by our output yn. Here is our output, okay, xn. So first we have 1, so we enter with 1, okay, sum plus with, so we have 2 times of our x z minus 1. So z minus 1 delay element multiply with 2, so plus up. So we have done part 1 and part 2. Then we will go to z minus 1. Okay, go down with minus 3, multiply with minus 3. So z minus 1, minus 2. So we will have negative 3, z minus 2 plus. Okay, then we go to minus 4, z minus 3, okay, minus 1, minus 2, minus 3. So multiply with z minus 4, sum up. Then we go to the last one, plus with 5, z minus 1, minus 2, minus 3, minus 4. Okay, we sum up. Then we go to the output. So this is just very easy for the direct form. For cascade form, we have to be careful. When we have one direct form, this one is our general equations. So this in general functions, differential equations, we will have to factorize it into a two form, into two. So this two is z hash jack 1 plus 2z minus 1. They multiply with 1 plus with 1 over 2 z minus 1 plus z minus 2. Okay, when we expand it, we will get back the above equation. So if you multiply 1, 1, you will get back 1. So 1 with 1 over 2, we get 1 over 2. Another one, so we will have 1z minus 2. Then 2, we multiply here, we will get 2z minus 1. Okay, so we will sum up with the previous one. Okay, then this one multiply with 1 over 2. Okay, and then multiply with 2z minus 3. So we get this one. So which means it's the factorization. Okay, after we factorize out, we will have z hash jack 1, hash jack 2. So first we brought hash jack 1 and then we brought hash jack 2. So for the hash jack 1, we have an input xn, so go straight, we have 1, okay, plus up with 2z minus 1. So summation, okay, then we go straight. So here we have 1, growth rate is 1. Summation with 1 over 2. So here 1 over 2 multiply with our z minus 1, z minus 1, sum up. And then the last one is z minus 1, z minus 2, multiply with 1. Okay, sum up. Then we go to the output. It's a very easy realization. After that, okay, to design the FIR in Matlab, how? Okay, so we will have the functions, Matlab functions, which is n omega n beta f type equals to Kaiser order. This one is a Kaiser window. If you want to design by using Kaiser window, you will using this one. So F, A, D, E, V, F, S. So find an approximate order n and normalize frequency band h of Wn. So this one is F, is a vector of the band h. So this one is our vector for the band h. So involve the parameter of pass band and the stop band h. Okay. A here is the vector defined for the amplitude on the band defined by F, typically value of 0 and 1. Okay. DEV here is the vector of the maximum ripple. So DEV, which means the ripple in dB. Fs, as we know, is a sampling frequency. And then we also need to use another, is this one, B equals to FIR1. Okay, this function is to design the FIR function. Okay, SIR filter function. We design a low pass, high pass, band pass, or band stop by a multi-band filter is depend on the value of F type. So when we are changing this F type to high, it will become high pass. When you change it to stop, it will become band stop, and etc. Okay, so the number of element is Wn. Here is the number of element. So now we will go to questions. Okay, this is the example exercise FIR filter design. Using the functions of FIR1, design a linear phase FIR low pass filter meeting with this specification. So it's given the specification, pass band is 2 kHz, stop band H is 2.5 kHz, frequency rate is 10 kHz, and our band pass band ripple is 0.005, and stop band ripple is equals to 0.005 as well. So now we have to plot the gain, phase response, and we have to show the filter coefficients in a tabular form. And then we have to identify whether it meets the specifications. Okay. If not, we have to adjust the order and etc. in order for it to meet the specifications. Okay. Now we go to our Matlab. Okay, this is our code. First, close all, clear all, and CLC. Okay. Then we will have design the spectrum by given in the questions. So we can see here, inside these questions, we have our band H is 2K Hertz, so 2K, 2.5K FS, our stop band H, and we will have FT, sampling rate is 10 times 10, 10 times 10 power of 3, 10 Ka. Then we will have our stop band ripple, okay, 0.05, and pass band ripple 0.05 here. Okay, we just fill up the value. Now we have to estimate the order using the Kaiser functions. So we are using the FH, FP, FS. So this one is frequency H, FP, FS. So A, AVAL. So this one is our gain is 1 and 0. Okay, DEV. Okay, deviation which means is our ripples, RP and RS. And Fs is our sampling frequency, so equals to Ft. Then we just equal our n, omega n, beta, F type, our Kaiser order. So we fill in our age, well, aware, and DV and Fs. Okay, so now we are design the filter by using, if we didn't set anything, by default is a humming window lah. So if we set anything, it will have the windows. So H equals to FIR1 n comma WN. So for here, if you want to find what is Kaiser order, so we can just go here, so enter. So it will come out what is Kaiser window, and we can see what is Kaiser window. All here have the explanations of your value. And here have some example code how we want to do the Kaiser window. And this one is one of the example, magnitude and phase. Okay. So for example, if you want to find just now the FIR, okay, FIR1. Okay, this is FIR1. So it's a window-based FIR filter. So you can put in here N, WN, okay, F type. So you will, this one is high pass, low pass, or etc. So depend on the, then if you have comma window, okay, this one comma window, it will divide what type of window that you want to use. So this one is the example code. So this one is distribution window. So we can set our, okay, this one is high pass filter. Okay, this one our value just put inside. Okay. Okay, this is some of the example signal. Okay. Now we go back to our Matlab. Continue. Okay. So this one, next we will show the numerical coefficients. Display numerator coefficients are. Then we use display H. So DISP, which means it's display. Then we compute and plot the gain. So G stands for the gain, W. So we are using, okay, this one frequency, okay, H1256. Okay, so this one actually is the frequency response. Frequency response, our digital filter. So for this one, okay. Okay, then we are plotting our, okay, figure 1. So we are plotting our gain, response. Figure 2, we are plotting our phase, response. And figure 3, we are testing did we meet the specifications. Okay, to determine did we meet the specifications, so we are putting the magnitude H as a value of G. So we're putting the T1. So T1 is 1.005. So which means is we take 1 plus with the 0.005. So one length of W, then 0.0995. So after minus with this one, okay, then and 0.05. Okay, then we plot in our figure, then we plot. Okay, so now we execute and see how. Then we plot this one, WPI, MG, WPI, T1, WPI, T2, WPI, and T3. So now we execute. So after execute, we will have 3 figure. This is our first figure, is our gain. Okay. Then we have our second figure, is our phase response. And we have our third figure, is whether you meet the specification or not. Okay. So 1, 2, 3. Okay, 3 figure. So this one is our gain response, phase response, and the last one, whether you meet the specification or not. Okay, so this one we can see our gain is 1. So this one is our cut out in the middle. Okay, frequency. Okay, so done for that question. So you can repeat this Kaiser window with Butterworth filter, with with the other windowing, like rectangular, okay, humming window, and humming window, Bregman, and better. Okay, that's all. Thank you for today, and remember to subscribe my channel, okay, and click on the bell for notification. Bye.